the first thing I'm going to do to try to illustrate the idea of quantum numbers is by actually writing down the address of our school. All right, so here's our address of the school. So it's 5100 Ramsey Street, Fayetteville, North Carolina, 28311. Okay, so here's the address of our school. So let me ask you, Elena, if you can you summarize this address using 4 terms, 4 items, or 4 categories, such that you give me those 4 items, I can get the address?
So, like the 5100 Ramsey Street is one part.
Okay, what will you call that? Street, okay. Okay, give me 3 more.
And then the city.
City, Fayetteville. Okay, 2 more.
State.
State.
And
Zip code, okay. Street, city, state, zip code. So the idea here is that if you give me these 4 items, I should be able to find the address, okay, right? The location. So these 4 things gives me the location of the school where we are at right now. Okay, similarly, there's 4 numbers. Okay, 4 numbers. We call them quantum numbers. Okay, there's 4 numbers that describe the location. I'm going to put the term location in quotation marks. Okay, sort of the address or the location of an electron. Okay. Now the reason why I'm putting location in a quotation marks is 2 things. Number 1, electron is really not something that is location, because it has a wave and particle duality. So because the wave is oscillating and always moving back and forth, it's hard to really discern or get a location. And it's a particle buzzing around, so it's also hard to get a location. However, having said that, there's 4 quantum numbers that sort of determine the location. The fact we can never get a precise location is Heisenberg's uncertainty principle. It just tells us we'll never know the true location of an electron. Let's say if we want to figure out the momentum of the electron, okay, we will not know its position, where it's at. If we know the position where an electron is at, we will not know where it's going, even though electrons are always moving around. So to get one information, we sacrifice a piece of another information. And that's basically, in a nutshell, what Heisenberg's uncertainty principle states. That is to say, we never get, you're right there. You are right there, Elena. You can't say that for an electron, because it's always buzzing around, moving around. Okay, so that's why there's a certain uncertainty. There's a probability. See, you're 100% right there. You're 100% right there in that corner. Electron, you can't say that. You can say 90% there, 50% there. But there's an uncertainty, and that's essentially the Heisenberg uncertainty principle. All right, so what are these 4 quantum numbers? So this is what I want to explain, then electron configuration, and then we'll be done. Okay, the 4 quantum numbers to find the location of an electron are n. Okay, I'm sorry. Let me cross that. Sorry about that. Okay, the 4 numbers that determine the location of an electron are n, L, okay, m sub L, okay, and then m sub S. Okay, N, L, m sub L, and then m sub S. Like you gave me these 4 items, I got the address of the school. I should be able to give you these 4 numbers and you'll get the address of an electron, again, quote unquote. All right, so this is a little complicated, so let's do the easiest thing first. Okay, the easiest thing first is this m sub S. Okay, so this is called the spin quantum number. These are all quantum numbers. Okay, actually it's a magnetic spin quantum number. So imagine if you put an electron in a high magnetic field. You put this in a magnetic field, the electron. It will either orient with the magnetic field, okay, with the magnetic field, or it will go against the magnetic field. If it goes if it orients with the magnetic field, we call that spin up. So that's 1/2, just plus 1/2. If it orients against the magnetic field, it's spin down. All right, n is the second easiest quantum number. This is called the principal quantum number, and it's easy. Okay, it's easy. It's basically the row in the periodic table. Okay, so principal quantum number is the row. Okay, so this is row. Right, so this is row 1, that would be n equals 1. This would be row 2, n equals 2. Row 3, n equals 3. Row 4, n equals 4. So it's just the row in the periodic table which the electron resides in. So the first quantum number is n. The fourth quantum number is either spin up plus 1/2 or spin down minus 1/2. So this L and M sub L is a little bit more complicated. So let's spend some time doing that. Okay, so here we go. It's N, L, M sub L, M of S. Okay. So the first thing I want to tell you guys is that these electrons, the location of the electrons, they're housed in orbitals. They are housed in orbitals. So these orbitals have different shapes and sizes. Electrons are going to be housed in orbitals. So let me show you or give you the names of these orbitals. Okay, we have an s orbital. Okay, that just has 1 slot. We have a p orbital. This has 3 slots. Okay, this p orbital has the shape of a dumbbell. The p orbital looks like, or the probability of finding an electron is in the shape of a dumbbell. Okay, a dumbbell along x, a dumbbell along y, and then a dumbbell along the z-axis. The s orbital looks like a sphere. Okay, the probability of finding an electron is a sphere, a big circle sphere of electron density. And then there is d orbital. D has 5, and they're all weird shapes. It's on the next page for those following the notes. The d orbital has 5 slots. 1, 2, 3, 4, 5 slots that can house electrons. And then I'm not going to talk too much about this, but there's F. F has 7 slots, and the shapes of each of these F orbitals are way beyond my mind and cannot comprehend, because it's like difficult to, the shape is difficult, but it's 7 slots. 1, 2, 3, 4, 5, 6, 7. Okay, the F electrons are these elements down here. Let's get your periodic table. These elements here, the electrons go to the F orbital. 4F, principal quantum number 4. The elements here, these electrons go to the F orbital. 5, principal quantum number. Here, the electrons go to the D orbital. Here, the electrons march to the p orbital. Here, the electrons march to the s orbital. Okay, they march in a very specific order. Okay. So what is this L then? Okay, that's what I want to talk to you guys about, this L. So this L tells you the type of orbital. So you're going to have to memorize this code. Okay, you will have to memorize this code. If we're talking about an s orbital, remember the electrons go marching in. The electrons go marching in. So if we're talking about an s orbital, L is going to be 0. Okay, that is the code, or that's the key for S, which looks like a sphere. Okay, it's shown right here. Probability of finding an electron resembles a circle, resembles a sphere. Okay, so that is the code for an s orbital. If your L is 1, okay, you just have to memorize this code. Okay, that's the code for a p orbital, which has 3 slots, 1, 2, 3, and then the s orbital has just 1 slot. If L equals 2, we're talking about a d orbital. And remember, the d has 5 slots. 1, 2, 3, 4, 5. Okay, again, you just have to memorize this. And I'm not going to mention this, okay, not on your test. But if L equals 3, we're talking about an f orbital. Okay, the electrons go in 7 slots for the electrons to go in. 1, 2, 3, 4, 5, 6, 7. So that is our second number, L. Now let me talk to you guys about the third number, m sub L. Okay, if L is the house, the orbital is the house, then m sub L is the room. Okay, is it the kitchen? Is it the bathroom? Is it the living room? Is it the TV room? Okay, the position in the orbital. M sub L is called the orientation quantum number. M sub L is called a magnetic spin quantum number. This is the spin quantum number. L is the orientation angular momentum quantum number. You don't have to know these words, the specific words, but I'm just telling you the specific names they give these orbitals, or these quantum numbers. Okay, so m sub L. You see there's only one orbital here for the s, so m sub L is going to be 0 because there's only one slot for the electrons to go in. So m sub L will be 0 because there's only one slot for the electrons to. So L is 0, m sub L will be 0 for. And you just go. It's a one-room closet. There's no other space for it to go. Okay. But let's talk about a p orbital now. M sub L. Okay, here it's going to be 0. For a p orbital, we take the center slot and make it 0, and then we number it from left to right. +1 going this way, -1 going that way. So the p orbital can be -1. The electron can go in -1. Think of it as the kitchen or the bedroom or the bathroom. It can go into the 0 slot. Remember, the center always gets 0. The center slot, the center shell always gets 0. And then we just do it numerically. So the m sub L for a p orbital, this is the shape of a dumbbell, remember, it can go to -1, it could be 0, or it could be +1. Okay, m sub L, the third quantum number. Right, the center always gets 0. The center always gets 0, and then we just count numerically. Okay, so +1, +2, -1 going to the left-hand side, -2. So that is what m sub L can be. M sub L can be -2, or -1, or 0, or +1, or +2. And though I'm not going to talk about F, again, same principle here. 0, it gets the center slot, and then we number it left and right. Okay, so we can be +1, or +2, or +3, or -1, or -2, or -3. So that's what m sub L can take. Okay, this is called the magnetic quantum number. Don't worry about the technical name. It's just where within the orbital can it reside. So these are the different values of S, P, and D. And of course, the fourth quantum number, spin quantum number, is +1/2 or -1/2. Right, here's how the electrons are going to go. Okay? So the electrons go marching in. Okay, you heard that song? The ants go marching in. The electrons go marching in. Hurrah, hurrah. Okay, hurrah, hurrah. This is how they march in. Okay, for S, they're going to go spin up, and then they're going to pair and go spin down. For S, because it's so close to the nucleus, it's like front row. So if it's front row, they're going to sit by each other. Okay, for the p orbital, a little bit out, it's going to go spin up, and then spin up, and then spin up. Instead of the electrons moving to the next higher level, they're going to pair. Okay, imagine going to the basketball game. I'll sit by you because I want to see the basketball match. Okay, I don't want to go back up and sacrifice my view. So instead of going to a higher level orbital, it will pair spin down, spin down, spin down. Okay, for the d orbital, it's the same thing. They're going to go spin up, spin up, spin up, spin up, spin up. And instead of going to the next energy level, they'll pair. And then they'll go spin down minus 1/2, spin down minus 1/2, spin down minus 1/2, spin down minus 1/2, spin down minus 1/2. So that is how the electrons are going to go in P, D, and F, not in S, because this is like front row seats. Okay, so they'll pair. Okay, but P and D, they're going to kind of move away from each other only before they come in pair. This is called the Pauli exclusion principle. Okay, not something you need to know, but I'll just throw it out. Okay, spin up, spin up, spin up, spin up, plus 1/2, plus 1/2, plus 1/2, and then they'll pair minus 1/2, minus 1/2, minus 1/2. So really quickly, what do these look like? Okay, the s orbital looks like a sphere. All right, the principal quantum number here, 1s orbital, is going to be 1. Principal quantum number for a 2s orbital, n is going to be 2. Okay, remember, n, l, m sub l, m sub s. Okay, here the principal quantum number is going to be 3. Okay. Higher energy levels, farther away from the nucleus. Okay, what is L for an s orbital? L is 0. There's only one slot. Spin up, spin down, so m sub L will also be 0. P orbital, remember your key here, L equals 1. And again, here's your dumbbells. Okay, dumbbell along X, dumbbell along Y, dumbbell along Z. Right at the center is a node, 0 electron density. Okay, right at the center is a node, near 0 electron density. P has 3 slots, L equals 1 for P, but M sub L, you see it can go to 0, plus 1, or minus 1. And within 0, plus 1, minus 1, it goes spin up, spin up, spin up, spin up. Spin down, spin down, spin down. Okay, here, this is an n equals 2 energy level. How do I know it's n equals 2? It's 2p. Okay, for the d orbital, L is equal to 2. D has 5 slots. 2, 3, 4, 5. Okay. What is the principal quantum number? Here, n is equal to 3. Okay, how do I know n is equal to 3? Because it's a 3D orbital. 3D, 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 3D. Look at the crazy shapes of the d orbital. Okay, really weird shapes. Probability of finding an electron density. All right, m sub L for a d orbital. It can be 0, plus 1, plus 2. It can be minus 1, minus 2. And then how do they march? Spin up, spin up, spin up, spin up, spin up, spin down, spin down, spin down, spin down, spin down. Okay, so let's really consolidate this and make this more clear. So for better clarity, let's do some problems here. Page 13. Right, so something like this on the quiz or the exam, how will you tackle this? How will you tackle this problem? So it's asking for it's asking for the 4 quantum numbers for an electron in a 3p orbital. Okay, so remember again, 3p. So right off the bat, you should recognize n is equal to 3. Okay, right off the bat, you should recognize n is equal to 3 because it's a 3p orbital. Okay, recognize that p has 3 slots. Recognize that P has 3 slots. Remember, dumbbell shape, dumbbell along X, dumbbell along Y, dumbbell along Z. So our first number here is going to be 3. What is L for a P orbital? Okay, what's L for a P orbital? What's L for a p orbital? 1. How will the electrons go? Okay, they're going to go spin up, spin up, spin up, and then spin down, spin down, spin down. Okay, what is m sub L, our third number here? Remember, the center always gets 0. The center slot always gets 0. And then this becomes plus 1. We go sequentially. Plus 1 and then minus 1. Okay, so let me put a dot here. Okay, what is the address for this electron? Okay, it's 3. L for a p orbital is 1. Okay, what is m sub L? -1. Is that spin up or spin down? Spin up. Okay, pointing up. Okay, so that's the address for the first electron. Okay, we have 5 more to go. How about this one with the red dot? Okay, what's the principal quantum number? 3. What is L for a p orbital? Where is it residing? M sub L is -1. Is it spin up or spin down? Spin down. Okay, so that's the address for this second electron. All right, let's do the address for the purple one here, the third electron. All right, what's the principal quantum number here? This is purple. Okay, 3. What's L for a p orbital? 1. Where's this residing? M sub L in the orientation. 0, is it plus 1/2 or minus 1/2? Spin up. Spin up is plus 1/2. And then the gray one is exactly the same except it's spin down. So everything is the same except it's spin down. All right, so we got 4. We got 2 more to go. Let's make this one green. Okay, principal quantum number is 3. For a p orbital, L equals 1. M sub L, this is now in the 1 slot. And then it's spin up, so that's plus 1/2. And then let's make this electron a star. And the star electron here is everything is the same except it's minus 1/2. Okay. So those are the unique address of each electron in the 3p orbital. So this answer will have 6. This answer has 6 terms, each term with 4 numbers, because the address of an electron is 4 quantum numbers. Right, so that's how you approach this problem. All right, how about a 4d orbital? Okay, so right off the bat, n is equal to 4. This is energy level 4. The 4 quantum numbers are n, l, m of l, and then m of s. D actually contains 5 slots. So there's 5 slot 1, 2, 3, 4, 5. Okay. And what is L for a d orbital? Correct. L is 2 for a d orbital. L is 2 for a d orbital. Okay, so remember when you do your third quantum number, m sub L, the center always gets 0. That's the room inside the orbital. And then it's plus 1. You're going to just go numerically. Plus 1, plus 2, and then on the left it's minus 1, minus 2. Okay, how will the electrons go? Spin up, spin up, spin up, spin up, spin up. And then they pair, spin down, spin down, spin down, spin down, and spin down. All right, so this answer has 10 terms. Each term has 4 numbers. Okay, so I'll just number them. I'll just do dots. Okay. Yeah, okay, orange. Okay, orange. What's the address for this electron with the orange dot? 4, 2, minus 2 plus 1/2. Any disagreements? Everyone get that? Okay. Somebody speak if there's any harsh disagreements. Someone yell, scream. Okay, let's do the green electron here. It's exactly the same except it's spin down. Okay. Let's do the black electron, the black dot here. 4, 2, that stays the same, but you see it's now in the -1. The principal quantum number is -1 here, and it's spin 1/2. And then this electron here, I'll do a square. Okay, this square electron is exactly the same position, except it's -1/2. Okay, so that's the address of the square electron. Let's see, what else? How about purple? Okay, the purple electron, it's going to be 4, 2. This one is 0. Everyone see that? 0. It's spin up, so that's +1/2. Let's do a purple square here. Hopefully you guys are following. 4, 2, 0. It's -1/2. Okay, so we're sort of, what's the word? Getting the addresses. Getting the addresses. All right, how about the gray circle? The gray circle, it's 4. L is 2 for a p orbital. And then it's +1. And then +1/2. Okay. How about the gray square electron? The gray square electron is 4, 2, +1, -1/2. How about this pink electron here? Pink dot. That pink electron there with the pink dot is going to be 4, n equals 4. L is 2 for a p orbital. It's in m sub L2. And its spin up. Spin up is the same thing as +1/2. And then finally, we'll do a star here. Okay, the star electron is going to be 4, exactly the same. 4, 2, 2, but it's spin down -1/2. Right, so the answer for this is 10 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 terms, each with 4 numbers. Okay, so that is the answer for a 4D orbital. Okay, let's throw in something here. Okay, let's throw in 3s. Okay, so the quantum numbers for a 3s orbital. So automatically n will equal 3. So what does 3s look like? Okay, here's how the electrons go. They're going to go spin up. And then what? Okay, spin down. Okay, there's only one slot. All right, so what is, again, N, L, M of L, and then M of S? Okay, obviously N is equal to 3. We'll call this dot here. And what is L for an s orbital? 0. Okay, L for an s orbital is 0. 0, and if it's 0, there's only one slot. The third quantum number by default gets to 0. And what I have here is a +1/2 electron in the red dot. This electron with the red square is exactly the same, except it's -1/2. So that's what it would be for 3s. I'm sorry, 3s. You can do the same thing for 4s, 5s, 1s, so on and so forth. Right, so that's how we determine the location of an electron. Location, in quotation marks. Okay. All right, now we will wrap up this chapter with electron configurations. Okay. So the famous song, "The Ants Go Marching In." The ants go marching in. Okay, the electrons go marching in. Okay, the electrons go marching in. Hurrah, hurrah. Okay, so what is the order in which the electrons go marching in? That's important. The order in which the electrons go marching in. So the ants go marching in, hurrah, hurrah. The electrons go marching in, hurrah, hurrah. Okay, how will they march in? Okay, they're going to march in 1s, then they'll go 2s, then 2p, then 3s, and they'll march to 3p. You see, the order is important. After 3p, the electrons will march to 4s. Okay, something weird happens here. After 4s, where will they march to? The transition block, also known as the n-1 block. Okay. The D block is known as the N-1 block. Okay, they take the principal quantum number and subtract 1. So they'll fill 3D. Then after 3D, what will they fill? We go to 4p. After 4p, we fill 5s. After 5s, where do we go? The order is important. 4d. We fill up all 10 electrons of 4d. Then what? 5p. After we go to 5p, the 54 electrons of xenon, then where do we go? 6s. Something happens here. Everyone be careful here. After 6s, where do we go? This is the tricky part. After 6s, we go to the N-2 block. So after 6s, we fill up 4f, N-2. Now we go back, and what do we fill after 6s? 5d, very good. And then after 5d, what do we fill? 6p. After 6p, what do we fill? 7s. After 7s, what do we fill? Be careful now. I heard 5f, that's correct. We fill the electrons of 5f. After 5f, we go back. What do we fill? 6d. And then after 6d, what do we fill? 7p. So the order. Okay, the electrons go marching in. Hurrah, hurrah. But they're going to march in this order. 1s, 2s, 1s, 2s, 2p, 3s, 3p. I'm trying to make a song out of this. 4s, 3d, 4p. Okay. 5s, 4d, 5p. 6s, 4f, 5d, 6p. 7s, 5f, 6d, 7p. Okay. So that's how they march. Okay, so let's do a couple of these and see how this works. Okay, let's start out with hydrogen. Okay, how many electrons in hydrogen? How many electrons in hydrogen? 1. Okay, so hydrogen is easy peasy. Where will that electron go in hydrogen? Okay, it's going to go like this. So the electron configuration of hydrogen is 1s1. All right, what's the next element here? Helium. How many electrons in helium? 2. Okay, so where will that electron go? Spin down here, and then the electron configuration of helium is going to be 1s2. Okay. Notice that helium is a noble gas. We fill up the energy level 1. Is it not so? We filled up energy level 1, n equals 1 for helium. Okay. Did you guys have food? I want some food. I don't want candy corn. It's gross. They rot my teeth. Okay. All right, next one on this list here. Helium, lithium. Lithium. How many electrons in lithium? 3. Okay, so where will that third electron go? Right here. Okay, so 1s, 1 electron, 2 electron, 3 electrons. Okay, so the electron configuration of lithium is 1s2, 2s1. Oh, wait a second. What is 1s2? 1s2 is the same thing as lithium. Do you guys see this? Okay, the electron configuration of lithium, that's its nearest noble gas. Okay, so to fill up the 3 electrons of lithium, 2 of them from helium, and then 1 from lithium. So it's helium 2s1. All right, next on this list is beryllium. So that's 4 electrons. 1, 2, 3, 4. Beryllium is 1s2, 2s2. Okay, it's going to be helium 2s2. All right, from beryllium, we're going to go to boron. What do we fill after 2s? What comes next? 2p. Okay. So the 5 electrons in boron, 1, 2, 3, 4, it will go to 2p. Okay, so the electron configuration of boron is going to be 1s2, 2s2, 2p1, I'll just call it helium 2s2 2p1. All right, carbon is next on our list. Carbon, that electron, spin up, and then another spin up. So it's going to be helium 2s2 2p2. That's carbon. Nitrogen is next. So it's going to be helium 2s2 2p1 2p2 2p3. Okay, the electrons are marching in a very specific order. The electrons march one by one, hurrah, hurrah. 2s2 2p3. 2p3. Okay, let's go spin up. Now for oxygen, oxygen, it's not going to go to 3s, it's going to now pair up. Okay, why go to 3s when it can still be close to the action? Low energy. So oxygen is now we're spinning down. Oxygen is going to be helium 2s2 2p4. Okay, what's next here? Fluorine. Fluorine, 9 electrons. Okay, that's the 9th electron there for fluorine. So it's going to be helium 2s2 2p5. And now neon. Okay, neon is a noble gas. Why is neon a noble gas? Because see, the 10 electrons, they fill the n equals 2 energy level. So neon is basically helium 2s2 2p6, but basically it's just neon, okay? It's just basically neon because it's a noble gas. It's a fill n equals 2 energy level. Okay, same thing with helium, filled n equals 1 energy level. Okay, you've actually filled the whole shell, right? You filled all of the s and p orbitals of energy level 1 for helium. Neon, you filled all the shells s and p of n equals 2. Okay, so that's why these are noble gases. Okay, shall we continue on? Okay, sodium is at 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So sodium is going to be neon 3s1. Okay, what's next here? Magnesium is going to be neon, nearest noble gas, 3s2. Okay, remember the 10 electrons from neon, okay, plus the 2 electrons here give you 12. So 12 electrons of magnesium. Alright, this can go on, so on and so forth. Okay, so 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Argon has a filled n equals 3 energy level. Let's talk about potassium here. Okay, potassium. Okay, 19 electrons. So let's fill them up. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19. So potassium is going to be 19 electrons. So 18 come from argon, and then this is going to be 4s1. Okay, everyone see that? 4s1. So it's going to be argon 4s1. How about calcium on this list? Okay, calcium, 20 electrons. The 20th electron is going to go to 4s. Okay, so calcium, the electron configuration of calcium is going to be 18 from argon, and then 4s2. Everyone see that? 4s1, 4s2, 4s2. All right, now let's talk about this one here. Okay, let's talk about scandium. Okay, scandium. Okay, 21 electrons. What's the electron configuration of scandium? All right, we got the 18 from argon. 4s2. Okay, where will it go? 4s2, what's next? 3d1. Okay, 3d1. So the electron configuration of scandium. Okay, notice we're in the B block now. The electron configuration of scandium is going to be argon, 4s2, 3d1. 3d1. Okay, what about titanium? Argon, 4s2, 3d2. Okay? So the electrons go marching in. They are 3d2 here. That's going to be the electron configuration of titanium. Okay, so the electrons go marching in a very specific order. All right. Let me throw something in here. How about bromine? What's the electron configuration of bromine? Okay, we got 35 electrons. So 18 are going to fill up to the argon shell. Okay, argon. And then what? Where will they fill? 4s2, 3d10, 4p1, 4p2, 4p3, 4p4, 4p5. So the electron configuration of bromine is going to be argon, 4s2. Okay, the electrons go marching in. Hurrah, hurrah. 4s2, 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. Now we're entering into P territory, 3d10. After we complete 3d10, where do we go? Electrons go marching in. Hurrah, hurrah. 4p1, 4p2, 4p3, 4p4, 4p5. So it's going to be 4s2, 3d10, 4p5. That would be the electron configuration of bromine. Some people like to do this. You know, this is me, but this is also the right answer. But I like to put them in order. Usually 3 comes before 4 in terms of the quantum numbers. So, okay, both of these are correct answers. I just like to put the 3 before the 4. Okay, but you can put it like this. I like putting it like that because 3 comes before 4, but it's totally up to you. What do you think the electron configuration of bromine minus will be? Br minus. Okay. How does it become minus? Gains an electron. So the electron configuration of Br minus actually is krypton, so it becomes noble. Okay, that's why Br likes to be Br minus, because it gains an electron. Br minus now has 36 electrons. It has a filled, filled n equals 4 shell. Okay, so it's noble. So the electron configuration of Br minus is the same as krypton. It's a filled n equals 4 shell. 1, 2, 3, 4. Yeah, filled n equals 4 shell. Okay, we also call this isoelectric. Okay, isoelectric means same electron configuration. All right, lead. Let's do lead here. Okay, seems pretty complicated and messy. But how do we do this? Okay, lead. All right, 82 electrons. Okay, where will the, what's the nearest noble gas? Well, okay, the electrons go marching in. Hurrah, hurrah. They're going to march in. The first 54 will go into xenon. Is that correct? The electron configuration of lead will be xenon. That's 54. 6s2. Right after xenon, we got our 54 from lead. And then 55, 56. That's going to be 6s2. And then what? 4f. Boom, 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 boom. 14. Very good. Okay, we're filling after 6s. We fill the 4f. After 4f, where do we go? 5d. Okay, all the way up to here is 10, so 5d10. And after 5d10, we go back to 6p, 6p1, 6p2. So that's the electron configuration for lead. This is my preference. I like to put everything in order of principal quantum number. So this is just me 4, and then 5, and then 6. Okay, both are right answers, but you know, there's something about me that, since I guess I'm retentive or whatever the word is. I like the 4, 5, and 6 to be in the same order. But anyways, that's the electron configuration of lead. Okay, what would Pb plus 2 be? Pb plus 2 is going to be xenon. You're going to lose from the p orbital, xenon 4f14, 5d10, 6s2. Okay. You're going to lose from the outer. Remember, 6 is a higher energy than 5, right? 6 is a higher energy than 5. So if a bear is going to come in, is it going to come attack you guys, energy level 6, or attack us, energy level 4? More farther away, okay, it's going to release the electrons, those 2 electrons that are more farther away. Okay, so 1s, then 2s, then 2p, 3s, and then 3p, and then 4s. What happens after 4s? Where do we go? Transition metal 3d, then 4p, 5s. What happens after 5s? 4d, then 5p, 6s. What happens after 6s? 4f. Okay, the F block. Okay, after 6s we go to the F block, lanthanides and actinides. And then after 5f we come back to fill up the D. After 4f we come back to fill the D, and then P, and then 7s. After 7s, where do we go? Okay, after 7s we go to the 5f. We fill up all the 5f. We fill up all the 5f, and then we come back. Okay, we come back to the D, 6d, and then after 6d it's 7p. Okay, so the electrons go marching in, hurrah, hurrah, but they're going to march in, hurrah, hurrah, in this very precise order. Okay, very precise order. All right, last thing of the day, or last 2 things of the day here, so I appreciate your patience. Just a couple of more things. Everything is fine and dandy until we reach, unfortunately, copper and chromium. Okay, everything is fine and dandy until we reach copper and chromium. So let's talk about the electron configuration for copper. Okay, so I'm going to draw the scheme again. Okay, energy is on the y-axis. All right, how will the electrons go? Okay, so first 1s, then 2s, then 2p, and then after 2p they go to 3s. After 3s they go to 3p. Okay, after 3p they go to 4s and 3d and 4p. Okay, so I'll stop there. All right, so electron configuration of copper. All right, how many electrons are in copper? 29. Okay. Let's do chromium first. Okay, so let's just do on this side here the electron configuration of chromium. All right, how will they march in for chromium? How many electrons in chromium? 24. Okay, so let's do this. Ready? 24. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. You would think would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, so this is not the right answer. Okay, there's something really wonky, something weird with it, chromium. You see here, you look at this d orbital with me. It turns out that this just happens by itself also. This just happens by itself. One of this electron self-promotes. Okay, now you have a half-filled 3d orbital, and that's much more stable. So your book tells you that the energy between 4s and 3d is so small that just more stable this way. Okay, so the proper electron configuration for chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Okay. By the way, 3s2, 3p6, and all of that other stuff. Okay. The 3s2, 3p6, that's argon. So actually, let me make it a little more easier. It's going to be argon, because all of this is argon, is it not? Argon 4s1, 3d5. So that is the electron configuration for chromium. Okay, so basically it's a promotion to a half-filled 3d orbital. Much more better, much more stable. So it's going to be krypton 5s1, 4d5. And along the same vein, tungsten is going to be xenon 6s1, 5d5. Okay, following along the lines of chromium. All right, everyone see that? So this is just some exceptions. Okay, this is just a better energy. Okay, lower energy, more stable. All right, let's do copper then. Okay, copper. 5 more minutes. Yeah, how many electrons in copper? I think, Elena, you said 29 way back when. So let's do that quickly here. Copper, 29 electrons. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So you would think the electron configuration of copper would be, okay, so 3s2, 3p6 is argon. Okay? 3s2, 3p6 is argon. So you would think it would be argon 4s2, 3d9. But that's not what happens. Here we have a promotion. Okay, again, the energy between 4s and 3d is very, very small. I guess, like your textbook says, this just happens by itself. So this electron self-promotes to fill up. This electron self-promotes to fill up a 3d orbital. The electron configuration of copper is actually argon 4s1, 3d10. So again, we have a promotion. This just happens by itself. A promotion to a completely filled 3d orbital. So the right electron configuration for copper is 4s1, 3d10. It just happens spontaneously. Okay, so it's just much more energetically favorable. Again, this just happens on its own. Having said that, we can do the exact same scenario for silver and gold. Let's do silver. Silver is going to be krypton. Everyone watch. Silver is going to be krypton 5s1, 4d10, self-promotion. So silver, along the same ideology, is going to be krypton 5s1, 4d10. Okay, that's going to be silver. Everyone see that? And for gold, AU, 6s1, 4f14, 5d10 would be for gold. 6s1, 5d10. Okay, but actually, okay, if you want to be technically correct, it's going to be xenon 6s1, 4f14, 5d10, but that's a little too technical. But again, promotion to a completely filled 3d orbital, 4d orbital, and 5d orbital. Okay, here promotion to a half-filled 3d orbital, a half-filled 4d orbital, and here a promotion to a half-filled 5d orbital. So a little bit of the anomalies, a little bit of exceptions. All right, copper and chromium and everything below it. All right, just super quickly, give me 1 more minute of your time. The ground state electron configuration of phosphorus. Are we guys confident enough to do this? Okay, where is phosphorus here? Okay, phosphorus, 15 electrons. 10 of them are going to come from neon. Okay, after that, 15 electrons, so 10 from neon. Okay, 3s2, 3p1, 3p2, 3p3. So phosphorus is neon, 3s2, 3p3. Okay. right? Phosphorus, neon, 3s1, 3s2, 3p1, 3p2, 3p3. And then finally p minus 3, you gain 3 electrons. And when you gain 3 electrons, you become 18 electrons. You gain 3 electrons, you become isoelectric with argon. Isoelectric with argon. So I'll just write argon. Okay. Argon. So that means it's noble, filled, n equals 3 energy level, filled, n equals 3 shell, and isoelectric. All right, so that is electron configuration.